Well, this is Mark Uckefer. I'm Executive Director of the Fiber Optic Sensing Association, and welcome to our October webinar. We're very pleased to have as our presenter this month Dr. Gareth Lees, who has had an extensive history. I won't read his entire bio, but I will particularly note that FOSA has been very privileged to have him during the past year as chairman of our technology committee, which he's done extensive amount of work in advancing fiber optic sensing. This particular presentation is beyond DAS, advances in distributed Rayleigh sensing. Well, I won't get into all the details because I'll leave Gareth with some, but this presentation should leave time for some questions. So at the end, we'll be able to share information back and forth using the text box. So Gareth, we look forward to hearing your presentation.
Okay, fantastic. Thank you for the introduction, Mark. So my name's Gareth Lees. I'm the Research Director of AP Sensing. And as Mark said, I'm also the chair of the Technology Committee for FOSA. So if you have any kind of questions after the presentation about either FOSA or AP Sensing and our products, then please let me know. My email's on the screen. So the title of my presentation is Beyond DAS, Advances in Distributed Rayleigh Sensing. The title should become a bit clearer as we kind of go through the presentation. My intention is to kind of explore DAS, some of the history, and kind of where we want to go with DAS and where we want to go with distributed Rayleigh sensing in general. So my presentation's split into three roughly equal sections. There's probably 10 minutes or so just talking about AP Sensing as a company and what kind of products and services we offer, and where we've come from really, and what we're all about as a company. Then I'm going to talk quite a bit about the technology. It's obviously the bit which kind of interests me. So I'm going to talk about DAS, a bit of history of DAS, and where DAS kind of came from, and a bit of the terminology around DAS products. And I've put there phase versus amplitude, but actually it's a lot more complicated than that. And I'll try and explain a bit more about the differences in different DAS units. And then finally, I've got a kind of a case study about enhanced DTS, where DAS can help improve the performance of DTS, which is unusual if you consider DAS to be a distributed acoustic sensor. It's obviously much more than that, and kind of hence the kind of unusual title. So this is just a bit of background about AP Sensing as a company. It actually spun out of Agilent Technologies, but Agilent Technologies came from Hewlett Packard. Hewlett Packard is obviously, if you go back 10, 20 years, it was a test and measurement company. It's obviously moved on into other areas and passed the test and measurement baton over to Agilent Technologies, which has then turned into Keysight Technologies. So a number of changes of identity there, but the test and measurement kind of background is still there, and it's still in Bookham, actually, in the same building that AP Sensing. There's still Keysight Technologies, still producing test and measurement equipment. So we're in there with a good crowd of expertise. We've got a pretty global presence. As I said, the headquarters are still in the original Hewlett Packard building in Bookham, Germany. There is a facility in Basingstoke, which is where I'm based, which is predominantly signal processing, data science, and software engineers. But then around the world, we've got various operations and sales centers covering North and South America, the Middle East, and the Far East, including kind of China, Korea, and Singapore. So there's a kind of a diverse range of areas there. We cover quite a few markets. A lot of them are DTS only. So the obvious one on this particular slide is fire detection. It's obviously a big market for DTS. It's the kind of core area and core application for us. There's always a need for DTS products in areas such as tunnels, where you can run a fiber covering the entire length of the tunnel, and large infrastructure as well. So fire detection is kind of a core DTS application area, and power cable monitoring as well was kind of core DTS. If you go back even to the 80s, power cables were being monitored with distributed temperature sensors, primarily so that the loading on the cables could be controlled based upon the temperature of the cable. More likely now you would have DAS as well as DTS, looking for TPI events around your cable or faults on your cable. So although some of these markets were originally DTS markets, we're seeing a lot more DAS start to come into those kind of areas. LNG monitoring is again predominantly DTS, where you're looking for leaks within the annulus of the kind of storage vessels. Similarly with pipeline monitoring, sometimes you would have a DTS and you're looking for leaks in the annulus of the pipeline, but more often than not now, you would install a DAS and look for third-party intrusion events and try and predict damage before it actually happens using the acoustics in the area surrounding the pipeline. So some more application areas. Well and reservoir monitoring is for DAS. It's quite an exciting area, especially in this kind of seismic world. The ability of a DAS to measure the acoustic signature along the entire length of the fiber in one go kind of makes it well suited to replace or at least complement existing geophone seismic surveys, where you'd have to lower a geophone into the well, then gradually pull it out a bit at a time to take a measurement. With the fiber optics, you can get a reasonably good one component measurement along the entire length of the well in quite a short space of time. So on oil rigs where time is at a premium and costs a lot of money, fiber optics is actually is working quite well. It's got a nice application there. One I'm particularly excited about is train and rail monitoring, especially for DAS rather than DTS. The ability to locate and look at the velocity of trains and timetabling, that's exciting, but being able to look at track and train quality, so looking at whether there's cracks in the track or flaps on the wheels, that also is quite an exciting application within the train and rail monitoring area, and there's quite a lot of activity in that market at the moment. Geo and hydrological is also a market which has been around for a long time. Large civil engineering projects and large assets. Perimeter security, again, primarily DAS, looking for third-party intrusion onto critical areas such as airports, as illustrated by the picture there, but also critical assets such as other cables, critical cables, or borders, or anything where you have a very long length to monitor. DAS works pretty well in those kind of areas. So this kind of slide tries to explain a bit about the company as a whole and kind of our viewpoint. We're very much a technology-focused company. When the company started, we had a DTS technology based upon code correlation, which, if you're not familiar with DTS, is just a way of making a temperature measurement. If you go back 10 years, the ranges were quite short. An 8-kilometer system would be, quite a nice range to have for a DTS. But if you look at where we are now, 10 years later, in terms of range, we're world leaders, certainly for DTS, Raman-based DTS, where 70-kilometer single and multi-mode systems are available. But on top of that, we're on our third revision of DAS as well. So technology is kind of a real core driver for us. And I think that's kind of illustrated in the amount of our revenue we then feed back into R&D. It's if you look at a lot of other large technology companies, we're trying to keep up there. We're trying to invest in the development of pushing forward distributed fiber technologies, because it is a fantastic and exciting area to be in, and there's so much more to do in this kind of area. So that's just a kind of a slide just illustrating kind of the kind of growth in our technology going forward. So in terms of what we kind of offer, so obviously the core of our business is the instruments themselves. And although we have DTS and DAS, within each of those kind of categories, there's actually a large number of variants. So for DTS, we offer different numbers of optical channels. We obviously offer multi-mode versus single mode monitoring, but also we offer different ranges with different performance specifications at each of the ranges. And the same kind of applies to our DAS as well. Although we offer standard ranges for DAS, 20, 50 and 70 kilometers, we also have a high performance version as well, which has much higher underlying performance to give you the best quality DAS measurements you can, albeit at shorter ranges. So although there's 2 product ranges, within each of those ranges, there's actually quite a lot of variety. Moving forward from the instruments, we can take the instruments and we can package them in lots of different ways. And actually, although the instruments where all the technology is, a lot of the engineering effort is actually in installing it in a way which is reliable and robust. We offer wall-mounted solutions primarily for fire detection and the fire markets. We also offer ATEX enclosures for areas where there's gases or potentially explosive gases. We also have very low temperature enclosures down to -40 degrees C as well. On top of the enclosures, there's also a need to provide rack solutions. In this particular picture, there's a project which requires 5 racks. Within each rack, we can offer different redundant systems. There's obviously a lot of different ways to carry out the networking and the control of data, on top of uninterruptible power supplies, different backup solutions for the data which we collect with our systems, and obviously different levels of operator display as well, and engineering displays. So it's quite a key part of our business and carrying out the kind of solution part of the business. On top of all this hardware, we're very much a software company, in that with even the best hardware in the world, if you don't take advantage of that hardware, and if you don't extract the value from your data, then it's, you're not providing the best service to your client. So at the kind of core of our software, we have a package called Smart Vision. And Smart Vision takes all of the data from DTS and DAS instruments, and it consumes all that data, and then it can provide different algorithms depending on which application you're in to process the data and extract the value. And we can also display that data in lots of different ways, either on an asset view or a map view or 3D map view or satellite imagery, and many different types of ways of displaying the data. But it also provides the interfaces with other systems such as CCTV camera systems, Modbus interfaces, OPC, many different protocols with which to talk to other parts of the system. It's also scalable, so you can have Smart Vision consoles in different areas of your facility. In control rooms, you can have operator terminals with limited functionality, and in the engineering areas, you can have different displays and different setups for your Smart Vision. Behind Smart Vision, actually at the kind of instrument level, and I'm focusing a bit more on DAS now, there's an entire range of tools available to configure DAS instruments. And it's primarily come around because there are so many different application areas. Different application areas require different needs from the software and different configurations. So we have quite a powerful set of software behind, which allows you to set up based upon your fiber configuration, different rules. And the rules would be things like, is an event traveling with a certain velocity range? Is an event more than 50 meters long or less than 200 meters long? And is it a strong event, a weak event? What kind of frequencies does it excite? And that all is kind of common sense, but then underlying all of that, there are some very powerful machine learning models built into the software, which we can use to provide additional confirmation that what you're actually observing the signal from is what you're expecting. So the machine learning understands what mechanical digging looks like. It understands what cars look like and walking. And the machine learning part of the software then gives you a bit more confidence that what you're seeing is actually what we're telling you it is. So this kind of analysis and configuration tool is actually very powerful, and we can generate different machine learning capabilities depending on what particular application you're looking at. It's always good to have some videos, so I've got a couple of videos here. Hopefully they'll both work. So again, this is just different ways of visualizing data. Again, it's a train application. The good thing about trains is that they're pretty big signals. So the bottom left is a smart vision display. It's just a satellite imagery, and there's just two trains crossing. The top right display is more of an engineering display. It's just showing at the moment, scrolling onto the bottom of the display, a train leaving a station. Each one of the large circles there is a confirmed this is a train, and within each one of those kind of blobs, there's a lot of information about the train, such as the width, speed, the location, where it came from, and lots of other stuff as well. So the software is pretty modular, and it's designed to address a large number of different applications. And the way it's set up is pretty powerful to address different markets. Okay, so I'm going to go on to talk a bit more about DAS measurements now, and I've tried to put this in a kind of way that's reasonably easy to understand without going too deep into technical things. DAS and DTS, actually, for that matter, are both OTDR-based technologies. You both have pulses of light. You send these pulses of light down the fiber, and then you look at what comes back. And the time between sending the pulse of light and you getting a signal back, similar to a radar, gives you the distance down the fiber. For DAS, what we're looking at is a coherent Rayleigh effect. And from now on, I'm going to be trying to be quite careful with the wording I use, just so that when I come to some slides later on, you'll understand why. And the coherent Rayleigh effect is affected by minute changes in the optical path length of the fiber. And those optical path length changes can be caused by thermal, acoustic, vibration, or strain events. So the coherent Rayleigh effect is the underlying physical mechanism by which a DAS operates. We then look at this Rayleigh backscatter, this coherent Rayleigh backscatter, and we process the signals, and we then display those signals either in frequency charts or amplitude charts, illustrating then what that disturbance might be caused by. An example I usually give is if you have an idling engine, which is roughly 900 RPM, then that will look like a 15 Hertz signal. So by looking at the frequencies of the events, you can kind of draw some conclusions as to what it might be. So terminology, this presentation is actually the first time I've tried to put a slide together to discuss kind of terminology. And it's actually quite challenging. I mean, if you go back to 1984, people were talking about coherent Rayleigh noise and coherent fading effects for OTDR signals or backscatter signals. So even back in the 80s, the terminology was there to kind of explain some of the things we use now for acoustic sensing. And then if you kind of go forward from that, and again, some people might know some earlier papers, but the earliest paper I could find with distributed acoustic sensing was 2005. And distributed vibration sensing, DVS, was 2008. And then a lot of people now talk about amplitude-based DAS and phase-based DAS. And as I kind of went through and looked at all the different terminologies, I came to the conclusion that when I got to 22 different terms to describe DAS, I decided that actually there is no common phrase to really describe, or what would be the most common phrase to describe what we're actually doing. And it's a distributed measurement. There's no doubt about it. We send a pulse of light down and we look at what comes back. Therefore, it's a distributed measurement. All of the measurements rely upon Rayleigh. Certainly the ones I'm discussing today do. And we use it as a sensor. So the best I could come up with was a distributed Rayleigh sensor. And that then takes into account the physical mechanism we're using, but also it doesn't limit it to acoustics, because a DAS, or a distributed Rayleigh sensor, is not just an acoustic sensor, and it's not just a vibration sensor. It can actually do a lot more. And I think in order to do the technology justice, calling it a DAS is not giving it its full potential. So a bit more about technology and why some of the confusions kind of arisen regarding terminology. So on the right hand side at the top, we have an OTDR. Again, it's a Hewlett Packard OTDR, and that picture comes from the HP Journal in 1988. Below that, there's a picture of a typical backscatter, coherent Rayleigh backscatter, from a paper in 1984. And then below that, we have an original A version AP sensing DAS. Now, all three of those papers and products, they all use the schematic, or they all use the concept outlined in the schematic on the left. They all use a light source, they generate a pulse, and they look at what comes back, the Rayleigh signal that comes back. The difference between the conventional OTDR from HP at the top and the kind of two systems below is that the conventional OTDR might use an SLED, which is a broadband light source, and the coherent effects, as outlined by Healy in that Electronics Letters, and is used by the original AP sensing DAS from about 4 or 5 years ago, they use a coherent light source. So the difference in those technologies on the right hand side is purely the light source which is used. And if HP had used a narrow line width source in that top OTDR, they would have got a nice jaggedy picture, as shown in the middle there. So this is still a phase OTDR. So the AP sensing original DAS and Healy's paper there, it's still measuring the phase of the light, but within the pulse which you're sending down. So to all intents and purposes, it is a phase DAS, and it's a coherent OTDR as well. So if you say you have one of these instruments and you call it a phase DAS, that's perfectly correct. But nowadays, phase-based DASs, that term is being used for a more useful technology, and I'll go on to that in a minute. So with that previous technology, with the kind of the basic COTDR, if you take an input signal, you get an interference pattern, and what you get back is a speckly pattern. It's like if you shine a laser pointer at a rough surface and reflect onto a wall, you'll see a speckle, an interference pattern. The early fiber DASs were the same. You shone your narrow line with source down, and you'd get a one-dimensional speckle pattern back. You'd have high areas of intensity where the signal was constructively interfering within the pulse, and low areas of intensity where it was destructively interfering. Now, the problem with that is that within that transfer function, you apply an input signal. Depending on where it sits in that interference transfer function, you can either get the signal out, which you put in, which is if you sit at the quadrature point there, the midpoint of one of those rising edges, or you can get an inverted polarity, which if you're sitting on the other edge, or you can actually get twice the frequency if you just happen to be sitting at the bottom section here. And what makes matters worse is that this slope, so the sensitivity of your transfer function varies as well. So essentially, you've got a totally unpredictable output with relation to your input signal with this kind of basic DAS technology. It's fine if you want to know if something's happening. So you apply a signal. If you have your idling engine again sat there at 900 RPM, you would be able to see that something was happening. It might look like 15 hertz, it might look like 30 hertz. And you might measure it one day and you get a certain polarity. You might come back the next day, you would get a different polarity, or even a different frequency doubling would be higher than the fundamental. So the issue with that early versions is that what you get out isn't necessarily what you put in. All you can say is that you've put something in and you've actually got something coming out. So it's great for detecting things, but not so good for actually reproducing them. And actually, I've tried to explain something here, but if you've got access to the introduction on distributed optical fiber sensors by Arthur Hartog, there's a really nice picture on page 237, which has a great way of explaining in a bit more detail what I've tried to explain in this particular slide. So here's an output, an example of what that particular type of DAS signal looks like. So it's a very simple rock drop. We've dropped a rock on the ground, the cable's underneath it, and the signal on the left, the grayscale signal, yes, you can see something's happened. You can see there's large areas of intensity here. There's parts here where it's quite weak, and there's parts here where it's very strong, and again very strong here. Now, although the signal's strong on the output, that's not to say that the signal's strong in the ground. It's just to say that on the transfer function, it's at the peak. You're getting the most out for what you put in. So although the signal looks strong in places, that doesn't represent what's actually happening in the ground. So yes, you can see something's happened, but you can't really extract from the signal what the signal strength is in the ground. Not easily anyway. So moving on to kind of other different types of DAS technology, I'm going to explain a bit more detail about a technology called dual pulse technique. There are actually quite a few ways of doing this kind of concept. Dual pulse technique is one of them, and it's quite an early one from certainly the 1980s, 1988, I think. There's also interferometric receiver techniques, hexadyne techniques, homodine techniques, and many other different types of techniques for doing the same thing. Actually, the AP Sensing as a company don't use this technique, but it's really quite straightforward to explain. So I'll stick with it for the time being. So the way this technology works is instead of putting one pulse down the fiber, they actually put two pulses down, separated by a distance, maybe 10 meters. So you get effectively two backscatters, and those backscatters are slightly spatially separated when they get back to the receiver, but also they're at different frequencies. So what you get at the output is the difference in the frequencies. So I'll call it here the carrier frequency, and then an envelope. which is kind of the jaggedy appearance that you see on your amplitude traces. Now, the phase of this carrier frequency, we move on to the next one, the phase of the carrier frequency is proportional to the input signal. So you're looking at the difference in phase between two different locations, and that difference in phase is proportional to what you put in. So if you have an input signal and you look at the change in phase of this carrier, so if you measure the phase of this carrier signal, the change in phase of that carrier signal will be proportional to the input signal. Therefore, what you get out is what you put in. And if you repeat that experiment again, in fact, this was acquired simultaneously with the previous experiment. Both systems were run on the same cable at the same time. You'll see that you'll get a nice waveform. And where it's weak, it's where the coupling is weak. And it's a representative signal of what's actually in the ground. So it's a much better linear repeatable measurement, and you can do a lot more things with it. As an example, we kind of repeated that drop test 4 times, separated, I don't know, by 5 or 10 minutes. And you can then, because the signal's repeatable, you can just stack them, and you can just stick them on top of each other. So time, align, and stack. And you can see you get a really nice set of wavefronts. You can see signals where you couldn't see signals, and the signal to noise ratio of the underlying measurement is improved as well. So having that repeatability and that linearity opens up a lot more signal processing techniques. So this again is another example showing this is again is AP Sensing's early DAS at 25 kilometers. You can see that the signal on the plot on the left, it's kind of a bit bitty. It's not a uniform intensity along it, and it should be. The plot on the right is from a differential phase DAS, where we're doing this differencing in phase along the length. And you can see that the signal is a uniform strength along the vibration at that point, but also we're doing this at 49 kilometers, and previously we were doing it at 25. So although we call them both DAS, they're definitely not the same in terms of the signal quality and what you can do with the signal afterwards as well. So once you have something which is repeatable and linear, and you're happy that what you're getting out is pretty much what you put in, that then opens up an entire range of different ways of measuring what your system can do. So the plot on the right there is all of these measurements are from CFOM. There is a document called the DAS Parameter Definitions and Test document, which came out in 2018 from CFOM. Where the vendors all kind of got together and decided on a set of tests. So these are the kind of AP sensing outputs of some of those tests. We can measure the underlying noise repeatably. The plot on the right there, the one predominantly red, just shows the dynamic range of the system and the linearity of the system. And the ones at the bottom show the kind of spatial resolution of the system. And you can measure it on one day, and you can come back and you can measure it, and you'll get exactly the same results a week or 2 weeks, a month later. So you don't have any kind of variability within the system itself. It's a nice linear system. But what really is makes me kind of excited about this kind of improved linearity is that it makes your signal processing so much easier. If a signal looks like an event on one day and the same signal comes again a week later, it should look exactly the same. And if it does, then it just makes your signal processing so much easier. And it makes a lot of the machine learning algorithms and models we're looking at, they work so much better if the results are repeatable and are the same time after time. So in this particular schematic here, we've kind of got 3 potential events. The size of those kind of event clusters based upon the different features. If we had an older type DAS, they would be much more statistical. They would be bigger. There'd be more overlap. But with a modern DAS system, a linear DAS system, you can actually do a lot more clever stuff with the signal processing. So where are we going to go next? So this is just a plot showing, I've kind of switched over to the frequency domain. So most conventional DAS measurements occur between 1 Hertz and maybe 500 Hertz. And that's kind of where we were 5-10 years ago. That's kind of where the signals of interest kind of lie, with a lot of TPI activities. Going to much higher frequencies, I think, is quite interesting, but not because there are frequencies of interest there, but because if you can put more pulses of light into your fiber, you can generate a lower noise floors or improve your dynamic range. So there are reasons for sampling very quickly, and there is some work being done in various research institutes to try and push that higher frequency range, so we can put more pulses of light in our fiber. But again, it's usually not to pick up very high frequency events. It's to improve the performance of the underlying DAS. A lot of the really interesting stuff is being done at the low frequency end. And I've got the green and the red there, one for established markets, and that's kind of stuff which is, everyone understands, it's all out there, it's fine. A lot of the current activity is being done in the very low frequency end of the measurement, where you're looking at 0.1 Hertz, 0.01 Hertz, and even lower. So there's a lot of value down there, because although we call it a DAS, it does respond to temperature, it does respond to strain. And as I get a couple of slides on, I'll explain how we've used this kind of low frequency part of the distributed Rayleigh sensing measurement to actually improve our DTS performance. And again, if you go far enough, the kind of holy grail almost is to get down to an underlying DC measurement, where you can take a measurement of strain and temperature and know what the temperature is and know what the strain is, based upon the Rayleigh backscatter. But again, that's not a subject for this particular presentation. Okay, so enhanced DTS. So the final part of my presentation. So DTS, Raman DTS, it's a robust and reliable measure of the temperature of the fiber. What you get back tells you the temperature. It's a pretty fundamental measurement, and it works really well. The Rayleigh measurement, if you look at the kind of the changing phase or the changing optical path length of your fiber as a function of temperature, you can tell whether the temperature is increasing or decreasing by looking at the changes in the phase of your signal. So if you've got a good linear DAS, you can figure out if your temperature is increasing or decreasing. And if you combine the two together, you can use that DAS information to make your DTS measurement a lot better, and a lot better in two different ways. One is the DAS is sending a pulse of light 2,000 times a second, or even faster, and what you're getting back then is meaningful at those kind of rates. You're not having to average. So you have a very fast idea of what the temperature is doing, but also you can then, by looking at your acoustic sensor, by looking at your change in optical path length as a function of temperature, you can give an estimate as to how much the temperature is changing on quite a short time scale as well. So the combination of the two is actually quite powerful. Here was an experiment. I actually put this out and showed it about a year or so ago. It's a really simple experiment. It's a lab experiment. It was a DAS and a DTS, both on exactly the same fiber, with a hot plate and a technique for increasing the fiber up to 70 degrees C over a short period of time. So you just push a button and the temperature increases. So the plot on the left is your standard DAS output, and that's showing the rate of change of temperature. So it's almost showing the differential temperature. The plot on the right is another output of our system called DTGS, and that's the accumulated phase over a long time period. And if you look carefully, the peaks here of where the temperature is the hottest correspond with the center here. So this is where the rate of change of temperature is highest and the rate of decrease in temperature, but this is where the temperature is highest. So the two outputs are actually really nice. So you can see them quite clearly on the DAS. And that kind of started us off thinking what we could do with this. And this again was that output I showed about 12, 18 months ago. And we basically used the DAS measurement to compensate the DTS measurement. And again, it worked really well. The orange line is the compensated, and the underlying blue line is the original DTS measurement. So we thought, how far can we take that? And actually, I'll come back to this slide. In terms of how far you can take it, this was a similar measurement, but on a commercial basis. And this is at 69 kilometers. And the blue trace there is the DTS, and the orange trace is the eDTS. So we've taken a conventional DTS measurement, and then we've corrected the noise on the DTS using the information from the DAS. So in order, the kind of results we're getting there are on a measurement time of 30 minutes and a range of 70 kilometers, we're down to about 2 degrees C RMS noise on the eDTS measurement. And the plot in the bottom left is actually the original plot from Smart Vision. So the eDTS bit of code is in our Smart Vision software, and we feed in the DTS data, we feed in the DAS data, and it comes up with a better measurement of temperature. And that's a really good example of how we can modify a really nice temperature measurement to be even better. This actually shows, although the DTS is churning out a measurement every 30 minutes for these particular long ranges, this is actually showing the output of the DAS every 10 seconds. And as the temperature ramps up, you can see that this is going from 30 to 70. You can see you've got a really nice ramp. And then the top plot is a zoom in of that ramp. And it's basically showing what the DAS is providing every 10 seconds. So not only do you get a better temperature resolution on your trace, you also have this ability to look every 10 seconds and see what your temperature is. So you've got a much better measure of temperature resolution, but also of much shorter measurement time as well. Back to this trace. A lot of questions generally arise about how you separating temperature and strain out from each other. There's two really big things which go in our favor. One is that temperature changes are generally quite slow signals, just because of either the thermal mass of the cable or the thermal mass of what you're trying to measure. But also the changes due to temperature are typically orders of magnitude bigger than things you would see, for example, in third-party intrusion, or actually even in trains. So the two plots on the right are, we have big machine learning libraries, so I just extracted all of the data from trains and all of the data from cars, just to look at what the kind of signal levels were. And actually cars and even trains, they're fractions of a degree C equivalent temperature changes. So even though if a train went past, in terms of turning that into a temperature, it's still a small signal. So you're not really comparing like with like. So if you see a 1 degree C temperature change, that would be a huge signal, a huge acoustic signal to generate that kind of change in phase. We typically use a figure somewhere between 500 and 1,000 radians per degree C, which, if you're familiar with what DAS performance is, that's many tens of dBs above the noise level of a DAS. So in summary, DAS terminology can be very confusing, and it's come about because of the quite long history of DAS, and trying to differentiate all the different technologies. To be clear, not all DAS systems are the same. Although we call them DAS, they all work on very different, well, a lot of them work on very different principles. So it's worth trying to understand the kind of techniques people use within DAS systems. When the performance of the DAS is shown to be linear and repeatable, there are so many advantages to having that kind of technology within your DAS unit. From signal processing, from using that information to correct for temperature, for looking at strain measurement, all kinds of stuff become available to you if you have that nice linear measurement. And using that low frequency, what we've demonstrated is that if you use the very low frequency content of a DAS, you can turn a Raman DTS into something incredibly powerful at very long ranges. And you're getting down to kind of temperature resolutions, which are, become useful for a lot of different applications. And actually, we still think there's improvements to be made in the temperature resolution at that 70 kilometer. And just to finish off, I think this is a really exciting field, and it's evolving very rapidly, and there's many more really great things to come. So any questions? And I'll put my references in there as well.
Thank you very much, Gareth. We already have a number of questions, but if you'd like to join the queue, there's a text box to the right where you can type in a question. I'll deal with some of the procedural ones. Yes, the slides will be available. We'll actually be posting the entire presentation, which includes the slides on our YouTube site and our YouTube page, I should say, and our FOSA website as well, with a link to it. The use of conduit pathways typically is the preferred means of fiber cable deployments for many applications, certainly obviously in telecom infrastructure. What is your view relative to the ability of DAS in conduit to effectively work as opposed to a buried armored cable that's not in a conduit?
Great question, actually. In my view, I mean, the obvious thing to say is that we've done measurements on both, and conduits, yes, are used quite widely, and it's the obvious thing to do when you're taking measurements or you're carrying out installations, is to look at both the conduits and the direct buried. I think you do get different signals. There's no doubt about it. The signals which appear in a ducted cable will look different to a direct bury cable. And actually, when we were putting together our machine learning libraries, it's one of the things we have to have in there as to what is the cable deployment type. Is it ducted or is it directly buried? Saying that, a lot of the time there are certain circumstances where you would get a bigger signal if your cable was in a duct rather than directly buried. So it's not, you can't generalize and say a duct isn't as good as a direct bury. In fact, sometimes ducted cables provide better signals than direct bury, and vice versa. To me, they're just different. And I would say that DAS technology generally works with both. There may be very slight exceptions to that, but I would say they'll work with both in most installations. It's just the signals will be different.
And you can adjust for that. Thank you. This actually, well, let me just ask this. What is the life expectancy of the fiber optic cable?
Oh, wow. So I certainly know of cables which have been in the ground for many, many tens of years. I think it largely depends upon the environment and the construction of the cable. Having been involved with some very long subsea cables, if you put the effort in there, certainly many tens of years. And I'd be surprised if there was I wouldn't be surprised if there were cables out there which were 40, 50 years old. So yes, I don't, I think the surface equipment would need to be refurbished before the cable.
Sure. And actually, this is somewhat of a follow-up question, but actually from somebody else. Does the DAS technology primarily work on conventional fiber, or does it rely, or is it improved by enhanced specialty fibers designed to improve signal to noise?
It's again, it's a good question, and it's quite a
A loaded one. A loaded question. Go ahead.
It's yeah, no, it's for some applications, enhanced backscatter fiber will help. Generally, where you've got high losses, if you certainly with I would say some systems, if you took 10 kilometers of standard single mode fiber and then 10 kilometers of enhanced backscatter fiber, you probably wouldn't have seen much difference. Yes, you'd get a bit of signal back and you might have to turn your equipment down to compensate for the bigger signal, but where it works best is if you've got a 10 or 20 dB loss at the start and you're trying to boost a very low signal, then you can get some advantages over using enhanced backscatter fiber.
And I think the next one's more of a clarification question. Is the light source in the system a continuous or a pulsed laser source?
Okay, so in most cases, it's a pulsed laser source. There is some research out there which use a quasi-continuous but frequency swept source. But as far as I know, most commercial DAS systems use pulsed laser sources.
And how much of the sensing system relies on the performance of the light source, or I guess the laser? I'll stop there, yeah.
Yeah, I'd say that the lasers are actually pretty good now. So certainly much better than they were 10 more years ago. I think the limitation is not the laser at the moment. In fact, it's quite an interesting question for other reasons. If you take a cable and you directly bury it 1 meter below the ground, in most areas, the noise you see on your system will be the kind of noise which is generated which is there in the ground, generated by whatever else is in the area. And actually, if you have an isolated reference coil, when you attach the deployed cable, you'll just see a higher noise than your reference. So the limiting factor on a lot of these things is the environment you deploy the cable into, and not the system itself.
Now, here's an interesting question in terms of application. Is it possible to use the DTS technology or DAS technology to monitor outdoor conveyor belts with a big weather changing?
I think the environment is challenging. Anything where you've got the DAS, the underlying noise floor of a DAS is down to kind of picostrain or tens of picostrain. It's incredibly sensitive. As soon as you take your cable and you start to physically move it due to the environment, through wind and the noise from an active conveyor belt, as soon as you start to shake the cable, that is a huge signal as far as the DAS is concerned. And it becomes really challenging to do anything with those kind of signals and extract the kind of information you want from the cable actually moving around and being shaken by the application. I think if you could deploy it in a way that you had isolation from a lot of things and only looking at the things you want to see, I think it's probably bearings in this case, then it could work, but it's a challenging application.
Sure. Does the AP Sensing DAS interrogator flexible to adjust to the gauge length according to the application, and does it use dual pulse technique?
So yes, we can adjust the gauge length. That can be just adjusted in the software. When you're commissioning a system, the software enables you to set the gauge length. So it is configurable. There's no hardware changes. And no, we don't use the dual pulse technique. I think that there are a number of techniques, 3 or 4, and at their most basic level, I don't think anybody uses them. I think there's a lot more complex optical things you need to do to get a good DAS system to address things like fading, polarization fading, interference fading. There are a lot of things that people do now to optically to make a better system. So the kind of schematics which I draw up, they are very much simplified, very simplified versions of what most people use, I would say.
So DTS is normally done using fiber and loose tube cable. Does DAS provide a better signal when performed on cable where the fiber is within a tightly bonded jacket?
So if you're looking to, so there's 2 parts to that question, I think. If you're using the DAS to compensate for temperature, so if you're using the DAS in the EDTS mode and it's in a tightly buffered cable, then you'll need to allow for the thermal expansion of the cable as well. So I would say if you're in a EDTS mode and you want to use the DAS to get a better temperature measurement, then having it in the same kind of fiber in metal tube construction would be beneficial. The DAS does work very well in both fiber in metal tube and in a tight jacketed construction for normal DAS applications.
So I think I've been giving you some tough ones. So let me try and give you a little easier one, Gareth. For pipeline with mechanical joint connection, is it possible to monitor 24/7, 365 any change in temperature, strain, PSI, or the movement of the pipe?
So it's interesting about joints because one of the features we have in our software is to just monitor sections of interest. One of the challenges with DAS is that it does generate a lot of data. We actually have some systems in place to just look at particular areas. And it's for exactly this reason. If you're just interested in particular sections and everything else you're either monitoring with another technology or you're not really interested in, then we can pay particular attention and set up like I was shown in the software, you can set up different rules and different combinations of techniques to just look at those sections. So it is possible to make the system so that it focuses on just areas of concern. And some of the machine learning techniques we're using help in that regard as well. So it looks for changes rather than looking for specific things.
This probably will be our last one because we're coming up to the hour, but can you get good DAS signals with low coherence length lasers, or is the best signal with long coherence length lasers?
Interesting. So there's quite a bit of technology behind that. I think it does depend on what technique you use. Like I say, there's a large number of different techniques. I think you still need a certain coherence length of laser, but the underlying coherence length of the laser does not necessarily define your range, which might have been the case 5-10 years ago. That you couldn't exceed the coherence length of the laser, but that's certainly not the case with a lot of modern techniques.
Gareth, I'll confess we've got a number of other questions, but I'm afraid we're coming up to the top of the hour where we normally cut things off. Okay. I will say that you've got your contact information up so people can reach out to you. Obviously, some of the questions have been fairly detailed, fairly specific, and so that's probably the best way to handle that. But I will remind folks too that this entire presentation will be posted fairly shortly on our YouTube page and will also be available with a link off our website. So thank you for a very great presentation, Gareth. We've actually had, I think, one of our largest attendances so far. So certainly you created a lot of interest, and thank you very much.
No,
and
thank you.
that concludes this webinar.
Thank you, Mark.